Greetings. My name is Barrington Henry Jr. I am from Prince George's County, Maryland, and a senior at Morgan State within the chemistry department. The research that I conduct here at Morgan State deals with a emerging class of coordination polymers known as metal-organic frameworks. This class of coordination polymers is also associated with nanotechnology. I'll be covering metal-organic frameworks in the sense of biomedical applications, specifically their encapsulation of anti-cancer drugs and delivery and delayed drug release. The title of my abstract is Synthesis, Purification, and Characterization of Aluminum Metal-Organic Framework, MIL-160 towards encapsulation of anti-cancer drugs. I conduct this research under Dr. Alexander Samaklovov. So, metal-organic frameworks are classified as or associated with nanotechnology. These nanotechnologies are highly porous, very, very structured coordinated polymers, and are chemically and thermally stable as well. So metal-organic frameworks consist of a metal cation and an anion of an organic compound, which is used as the linker between the metal complexes. MIL-160 in particular is an unusual aluminum metal-organic framework with the linker of 2,5-FDCA, which is promising for encapsulation and release of anti-cancer drug molecules. Aluminum frameworks are of interest mainly due to their non-toxic nature. Metal-organic frameworks contain a special feature about them called pores. These porous areas serve as the means of a matrix by which encapsulation is achieved. So I've included a reaction scheme of 2,5-FDCA. So 2,5-furane dark carboxylic acid is mixed with a source of aluminum in the presence of a base, and figure A represents MIL-160, a molecule of MIL-160. When these molecules combine, we start to see these structures form in 3D space. These empty regions are pores. This is the areas by which encapsulation ensues. So as you see, initially they're empty, but later on they can be filled. So why encapsulate anything? Encapsulation of an anti-metabolite drug, for example, gamstabine, has many upsides to it, such as improved biodistribution, improved cytotoxicity, and protection against metabolic degradation. So the research fueling this project is how can metal-organic frameworks be implemented in biomedical areas, and specifically chemotherapy, to treat various types of cancer, but mainly focusing on pancreatic cancer. So methods, MIL-160 is synthesized by combining your source of aluminum, which is aluminum trichloride in our case, with the organic linker F25-FDCA in the presence of sodium hydroxide, which is acting as the base, water as the solvent. These, when combined, these are refluxed for a minimum of 24 hours at a temperature of 100 degrees Celsius. The MIL product, the MIL-160 product, is attempted to be purified via several centrifugation cycles using H2O as the liquid layer. Supernatant was saved for later testing. And after the supernatant layer was poured off and the MIL product was isolated, it was dried overnight at a temperature of 100 degrees Celsius. So instrumentation used to analyze the achieved product. Nicolet's IS-10 FTIR spectrometer. This FTIR spectrometer, as you see, has a blue spindle. Use the blue spindle to lower the needle onto a tiny portion of your sample, and the spectra is produced when ran. However, this spectrometer needs to be combined with a purge gas system that needed to be assembled. We purchased this from the manufacturer of this purge gas system is Parker Ballston. Generator model 75-45. Why is the purge gas system used? The purge gas system is used because it supplies carbon dioxide free air with very to little suspended impurities. and the generator offers cleaner background spectra in a shorter period of time and a more accurate analysis, because it improves the signal to noise ratio. So results: 455 milligrams of product was recovered, giving a 46% yield. When analyzing Figure 3, which contains both the furan dicarboxylic organic linker and the MIL-160 product, this is the spectra that was produced for both. So the dotted line represents 25-FDCA, and the solid line represents MIL-160. Peak 1 represents the characterization peak. This is how we know that our product was synthesized correctly according to some other known literature. However, characterization or vibrational bond assignment was not assigned, so some more analysis will need to be due to produce to be able to produce these results and correctly assign the bond responsible for this peak. If we look over here at Figure 4 is the numeric fitting of ATR, FTI, or spectrum of pure MIL-160 that was obtained in Part A of Figure 3. So molecule-molecule interactions decrease the frequency in splitting peak of carbonyl groups. What does that mean? So it was hypothesized that this peak right here is responsible for undissolved, a monomer of 2,5-FDCA undissolved. These peaks or portion of the spectra closely resemble this portion of the spectra. So it's assumed that some crystals are undissolved and also still entrapped within this MIL-160 framework. Discussion. This is a table comprised of the experimental data and published literature results of the spectra for 2,5-FDCA. When comparing the experimental data to the literature, to the published literature, it's noted that the results are pretty much the same. So, which is good, because that means that for accuracy purposes, we know that the experiment was done correctly. So, peak 1 is due to the stretching of a carbonyl group on either end of the 2,5-FDCA molecule. Peaks 2 and 3 are due to the carbon-carbon double bonds within the furan ring. 4 and 5 are due to the carbon-oxygen bond within the furan ring. 6, 7, or 8 are all due to the carbon-hydrogen bonds within the molecules. So this is a schematic that we're kind of representing some of the data that was found on Figure 4. Peaks 2 and 3 on the Figure 4 of MIL-160 graph is that the molecule-molecule interactions are known to lower vibrational frequency on the spectra. So we saw that the one area of the graph was closely mimicking another area on the 2,5-FDCA linker, meaning that, but at a lower vibrational frequency, meaning that there was most likely some undissolved 2,5-FDCA linker, monomer, or crystals within the MIL-160 pores. So conclusions: we successfully synthesized pure MIL-160 based on published literature sources. However, contrary to the published literature, it's believed that what they're claiming to be pure MIL-160 is not actually pure, because it contains these impurities of 2,5-FDCA in these two different forms, one being the monomer, one being crystals and trapped within the pores. So there's room for improvement there within the purification step of this MIL-160 framework. So in the future, also spectra will be produced for MIL-160 as well. If you notice, I didn't have a table comprised for you, because it would not actually be be able to be compared to anything because nobody has published literature for this. It's also believed that 2,5-FTCA is really hard to purify due to its nearly low solubility and attraction to just about any suitable solvent. So work is in progress to fully purify this MIL-160 product. Purity is mainly of importance due to the ultimate goal of it being able to be implemented in biomedical areas. It's very important that anything that's being used within the human body is as pure as possible, because we don't want to be introducing any impurities into living organisms, and undesired results are happening as a result of this. So I've also included a list of references for you all to view. And I would like to thank Dr. Angela Winstead for recommending me to be a part of this NIGMIS Rise organization, Dr. Alexander Semagov, my dedicated mentor, who's always consistently helping me, and Grace Navarro, who's one of the leading leaders in the NIGMIS Rise organization, constantly providing excellent guidance and outstanding leadership to the members of the NIGMIS Rise organization. Thank you.